Okay, so it's been like a long time. What were we doing last time? Aliasing, discrete frequencies.
The impulse train.
Impulse train, right, we did the impulse train. I think we started talking about the discrete Fourier transform last time. Does that sound vaguely? And I remember it was sort of a rushed affair, so why don't we kind of dig into that and talk about it a little bit more and then talk about some filtering, digital filtering. So believe it or not, there's a whole class that does discrete time circuits, discrete time signal processing, and I am not trying to eat into that class. I'm basically just trying to set you up with the basic knowledge, to tell you how continuous time sort of feeds into discrete time. Almost all the concepts are the same. They work almost identically, but there are a few nuances, and I just kind of want to at least make you comfortable with the fact that all the intuition that we've learned mostly continues on and applies very cleanly to the discrete time case. So you'll remember the discrete Fourier transform, the DFT. This marker looks like it's had better days. Oh, there's a difference.
Oh,
there is. It's a small difference, and am I getting this backwards? It's possible I'm getting it backwards because ultimately I don't really care. Yeah, I think actually you're right. I think the one we're doing is the discrete time Fourier transform, and then I'll explain if you want. I'll explain the difference in a minute, but it's a minor difference. Okay, so this is a discrete time Fourier transform, and basically the way it works is you say capital X of omega equals, we said it's the sum over all n, and then it's x of n e to the minus j omega n. Is that what we wrote down before? Okay, that's a good thing, right? Just we at least have the same equation. We can all agree on that. And again, what that does is it will take a signal and it will tell you the frequency content of that signal. And one of the nice things about this equation is that it correctly predicts the behavior for all discrete time signals if we look at the Fourier transform. Okay, what properties is it going to have? There's two properties in particular that we want to talk about, but what's every discrete time Fourier transform going to have in common? It's going to be periodic. With what period? It's like I'm at a bazaar. Do I have 2 pi? Do I have 3 pi? I have 3 pi. Can someone give me 4 pi? Okay, it's actually, there we go. Thank you. Sorry, had to get your quizzes delivered. Thank you, sir. Quit your whining. Quit your whining, or I'll give you an extra quiz. Okay, thank you, Alessandro. Okay, so first thing is it's periodic with period 2 pi. Okay, so if this is 0, this is 2 pi, and this is pi, and so we'll say minus pi and minus 2 pi. All right, so what?
You said that after pi it just repeats itself?
Yeah.
So you can't really tell if it is...
Yeah, it's always going to be periodic with period 2 pi. So for example, if I drew that, what else, and I said finish the diagram. Now let's say that was a quiz question. What would be the next thing I would draw?
Same thing on the other side of pi.
Right, so first things first, because we're looking at the magnitude, right, remember it's a Fourier transform, which is complex, so you're always going to need magnitude and phase. Right now we're just looking at magnitude. For the same reasons that we've been looking at this all semester, the magnitude plot is always even. So you're guaranteed to get that. Okay? What else am I guaranteed to get? The same pattern replicated at 2 pi. And, oh, well, I'm trying to make that a little bit more symmetric. And at minus 2 pi. Okay, it just goes on and on and on, repeating. Okay, so those are the two properties. One, it's even. Two, it's symmetric. It's periodic with period 2 pi. Now, what frequency does pi correspond to in going from continuous time to discrete time? With relation to the Nyquist frequency. Let's say we had a continuous time signal, we sampled it with f sub s. Right, so remember we have the conversion is omega equals 2 pi little f, which is the frequency of the signal that you're sampling, over f sub s. Okay, so I want to know, what does omega equals pi correspond to? So if I set big omega equals to pi, and I rearrange, so these cancel, and I rearrange terms, it looks like that corresponds to the frequency that was half the sampling frequency. And that's your Nyquist. Okay? So pi always corresponds to half your sampling frequency, which is also your Nyquist frequency. It's the largest frequency of continuous time signal you can expect to sample with this sampler without having aliasing. Right? So if I had a sampler, if I was sampling at 1,000 hertz, okay, this pi would correspond roughly to, would correspond exactly to a continuous time signal at 500 hertz. Okay? And if I try to put a 600 hertz signal into my sampler, then that 600 hertz signal would be indistinguishable from a 400 hertz signal. Okay? So whatever your sampling frequency is, you cannot go bigger than pi. Because once you go bigger than pi, you start repeating yourself. And pi is the Nyquist frequency. It's half of f sub s. Okay? So this is 2 pi corresponds to your sampling frequency and so on. Okay, but it's always periodic. Now what's crazy about all this is that this DTFT always, if applied properly, gives you a signal that is even and periodic with period 2 pi. It's crazy because you don't really look at that. There's no 2 pi hanging out there, but it just works, right? So if it doesn't work, you've got problems. But it does work. What do you think? What's the units of omega, big omega? Radians per sample. Suppose I have a signal with frequency pi over 4 radians per sample. What's the period of that signal? Suppose I've got x of n equals cosine pi over 4 n. What's the period? Right. Right. How many radians do I need to get a full period? Always. Always 2 pi radians per period. So if every sample, this is this many radians per sample. So one sample gets me pi over 4. 2 samples gets me pi over 2. 3 samples gets me 3 pi over 4. So how many samples do I need to get to 2 pi? 8, right. So the period is always going to be 2 pi over omega, which in this case happens to equal, did I do it right? I did. 8 samples. Yes, sir.
From that, how would you find the frequency of the region in the time domain?
Unless I tell you the sampling frequency, you can't know. You have to use this conversion, but you can't know it unless I tell you the sampling frequency.
But so if you sample with this, right, and it's not enough sample, and then it will change the frequency.
Then that's right, you'd have aliasing.
How would you know that by how much it changed the frequency and what is the new frequency?
Right. That's sort of the point of today's recitation. And I don't want to spend too much time on that just because I want to make sure that I cover other stuff here. But essentially the idea is you start by doing this calculation, okay? And then you look at your big omega and you see, is it less than pi? If it's less than pi, you're good. All right? If it's bigger than pi, then you have aliasing. And so what you do is the way I'd like to do it is I draw this picture. This is cosine of theta. And in the middle we have pi. So let's say you go and you do this calculation. You find omega equals 1.2 pi. Okay, so here's 1.2 pi. So here's cosine of 1.2 pi. And that happens to be the same as the cosine of, just by argument of symmetry, 0.8 pi. And that's the aliased frequency. And then you work your way backwards. So just hold that thought for a second. So, for example, suppose I'd sampled at 1,000 hertz. So what's the biggest frequency I can use if I sample at 1,000 hertz? 500. Okay. So suppose I violate Nyquist. Oh, lordy, how am I going to get... okay. So suppose I violate Nyquist, and instead of sampling a signal that's 500 or less, I sample at 600. So a 600 hertz signal sampled at 1,000 hertz. So I run the numbers and I get omega is 1.2 pi. Uh-oh. You look at this, you find out that 1.2 pi is indistinguishable from a frequency of 0.8 pi. In other words, if you were to go and make a table of cosine of 0.8 pi n and cosine of 1.2 pi n, right, for n equals 0, 1, 2, right, all the integers, you would find these are exactly the same. Not a little bit the same, not related. They would be exactly, decimal for decimal, the same. And that's the whole point of aliasing. Right. So now you work this backwards. You say, okay, if this is equal to 2 pi f over your sampling frequency of 1,000, solve for f. So the pi's cancel, and you're left with f equals 400 hertz. So in other words, I took a signal that was 600 hertz, I undersampled it, and it became indistinguishable from a 400 hertz signal. In other words, if I'd started with the 400 or if I'd started with a 600 hertz signal and sampled them at 1,000 hertz, I would get exactly the same thing. I would have no idea which one was actually, whether I'd started with the 400 or the 600. That's aliasing. You've not sampled fast enough, and that's how you do the calculation. You had a question, I'm sorry. Okay, come back. When you remember, you will remember. Okay, now what do we say the highest discrete time frequency is? Pi. So let's try this calculation again. Let's say that omega equals pi, the biggest frequency that there is. What's the period? According to my little formula here. 2 pi over pi? 2 samples. So let's draw let's draw the highest frequency signal there is. Okay? So there's a 1. What should I draw for my next one? My next sample? Sure, negative. Why not? Negative 1. What's my next sample? Right. See how it goes up, down, up, down? What's the period of that signal? Every how many samples does it repeat itself? 2. Therefore, that's what it looks like when a signal, a discrete time signal, has a frequency of pi. Pretty cool, right? Now, instead of 1 minus 1, what if it was 2 minus 2? Now what's its frequency? Have I changed the frequency? No, I've just changed the magnitude, but it's the same frequency. What if I do... Here's a fun one. What if I do this? I think that's it. Okay. Yeah, what's the frequency here? Still pi. What's different than before?
DC offset.
Ah! DC offset. Right? Frequency is still 0. Sorry, frequency is still pi, but whereas before the DC offset was 0, now my DC offset is... now my DC offset is 1. Right? The average value over one period is 1. And what's the frequency of a DC offset? Is 0. Okay, so in theory, if I were to take the signal 2, 0, 2, 0, and then just go on and on forever, I should see energy at 0, and I should see energy at pi. And where else? Minus pi, and 2 pi, and so on. Hold on a minute, this looks familiar. Weren't we arguing before about the Fourier transform of an impulse train? Is an impulse train? What do I have here? Fourier transform of an impulse train is an impulse train. Have a nice day. All right, should we do some examples? Okay. So let's...
So how did you find that it was pi or 2 pi?
Because we said that the frequency, the period is 2 samples. And when the period is 2 samples, that means that the frequency is pi.
So it repeats every pi.
Right, so I knew there had to be a peak at pi. Well, it always repeats every 2 pi. Every signal repeats every 2 pi. Okay? But it just so happens that the peak is at pi.
But in that case, the period will be n times the frequency,
Yes.
n times f,
No.
n times omega.
No. Yeah. Yeah, if this is n, n is your period?
No, n is just an integer.
Okay. Which plot are you referring to, the top one or the bottom one?
Bottom one, because it's repeating every pi, so...
It's repeating every 2... Well, okay. Let me pull the board down and I'll show you an example that will probably help clarify this, if I may. Mostly just because I feel like sitting down. Woo! Dim the lights a little bit. Okay.
The period is 2 samples, then you get 1 sample every other second.
There's no seconds anymore. I've sampled. As soon as you sample, the seconds are gone, right? Your x-axis is just in the units of time is just really samples. Yes, sir.
We know the big omega. Does that mean we have a relationship automatically between the time and the frequency domain? Because that's kind of what we did right there.
No, because if you know big omega, Remember, the best thing big omega can tell you is the relationship between the sampling frequency and the sampled frequency.
Okay. So, yeah, small f and big F.
Right, but it doesn't actually tell you the specific frequency itself, unless you know the sampling frequency, in which case you can work backwards.
Okay.
It's a little tricky. Okay, so let's start with this. Clear n equals 0 to 20. X equals cosine, let's say pi over 4n. Plot. Let's do stem, sorry. Okay, so here's a signal. What's on my x-axis? Samples. Is there any time in this? No, it's just samples, okay? So, what's the period of this signal? Right? It starts at 0, it peaks at 0, and then it peaks again at 8, and then again at 16. So it repeats itself every 8 samples. What is the frequency of a signal that repeats itself every 8 samples? We did that, right? Pi over 4 radians per sample. Well, here you go. Pi over 4 radians per sample. Now, let's add the Fourier transform of this. So let's see, x, what's the easy, let me think through this for a second. So x equals sorry, I'm just doing a little mental calculation here. Okay, let's do this.
Hold up.
What?
It's just a cosine, right? Shouldn't, it's just a cosine. You're taking the Fourier transform of a cosine. Shouldn't you expect 2 sticks?
Oh, good question. If it's just a cosine, shouldn't I expect a Fourier transform of just 2 sticks? That was actually what I was just going to demonstrate. Yes. Yes, what about n?
It's going from 0 to 20.
And?
So you're looking at multiple frequencies of the cosine. So you're going to get more sticks.
Almost.
Shouldn't you just see 0 at all frequencies that aren't the frequency of the cosine?
Depends.
It's an aperiodic signal, so you're not going to have that continuous.
Almost. You guys are all dancing around the right answer. Yes.
It's a periodic signal.
Okay.
So you're very close to a periodic signal, except for the fact that it's going to be finite, so you're going to get, I guess, like a whole bunch of sync pulses and stuff.
He's getting closest to it. Okay, let's look at the frequency axis. Okay, so let's say that I'm doing a little artificial thing here. This is not the way you would do this in real life. I'm just sort of going to write a little code here just to create a point. Yes.
I'm sorry. This is basically, it's like 8 of n, right? Looking at the harmonic frequencies. So it's like when you plug in like n of 0, then you have cosine of 0, which is 1. So you're basically whatever multiples end up having the power when you plug in n are the ones that you're going to see. Or you're taking the Fourier transform of these sticks.
Almost. Hold on. Let me plot it, and then we'll talk. Hold on. You guys are tantalizingly close. Okay. The vibrate feature on the phone is almost as annoying as the phone, the ring itself. Okay. So let's see. I'm going to take. Hold on. Let's see. X equals 0 for for I equals 1 to length of n. X equals x plus x of I times e to the minus j omega n of I. That should do the job, I think. Well, it didn't complain. That's always good. Okay, so figure 2, clear figure, plot W absolute value of x. Kapow! Okay, so we started with this signal. And then again, I want to emphasize, what I've just done here is not an example of anything good that you should do, but essentially what I've tried to do is just the discrete time Fourier transform, right? It's x of n times e to the minus j omega n, right? I've just tried to manually calculate it. All right, so let's look at that. And so what do you notice? Let's see. Let's zoom in a little bit and see if we can make some sense out of this. So, is it even? Right, that's the first thing we're supposed to notice. Yes. Good. Is it periodic with period 2 pi? Yeah, in fact, I can make it more obvious. If I take my x-axis and divide by pi, so now 1 will refer to 1 pi and 2 will refer to 2 pi. So, is it periodic with period 2 pi? Yes, sir. Very good. Okay. Now, is my peak where I think it should be? Where should my peak be? I have a cosine with frequency pi over 4. Therefore, my peak should be at, help a guy out, 0.25, right? Pi over 4, 0.25. Is that where it is? Sure looks like it. Let's see. Set, get current axis, x tick, 0.25. There it is. Okay. Now, the question came, why isn't it a perfect stick? It's just one frequency. Where's my stick? Yes! There we go. We've learned that you only get the perfect stick when you take an infinitely long signal. Have I taken an infinitely long signal? Of course not. Okay, I've taken a signal with 20 samples in it. So, if I change this from n equals 0 to 20 to 0 to 200, what would you expect to happen? It should be more stick-like. Okay, so let's try that. And I can limit myself here from minus pi to pi. Or actually minus 1 to 1, since I've divided. That did not do... Oh, because the xlim command didn't take. Minus 1 to 1... Is it more stick-like? Yes. Yay! Okay, good. What if I go the other direction, right? If I just go one period, I need to go 0 to 8. Actually, 0 to 7, right? That's one period. It's the same concepts as before, right? If you have a long signal, you have a better understanding of the individual frequencies. If you truncate your signal, you get sync pulses, which is basically what you're looking at. And you lose your ability to have fine resolution of knowing what's the signal and what's not. Okay, so let's go back to something nice and long here. Oh, that was 20. Let's go back to 200. I like 200. Okay. Now, if I change my frequency, if instead of pi over 4, I do the example where we have pi. Does what I'm looking at make sense? Absolutely, right? Here's your 0, the center point. The signal itself is at plus or minus pi. And then it repeats every 2 pi, so then you get your 3 pi.
Wait, when you do, I've got a quick question. When you do the fast Fourier transform, is this why, are you only considering one period?
That's part of it.
Okay, and that's why you have it at the edges instead of the middle?
Yeah, that's part of it.
Okay.
Right. That's like about 50% of the nuance of the FFT. The other 50% we can talk about in a second, or maybe on Wednesday. Okay, now, if I go back to my signal, I see that it's plus 1, minus 1, plus 1, minus 1. Shall I add a DC offset? Okay, so why don't I just add 1? So instead of going 1, minus 1, 1, minus 1, it goes 2, 0, 2, 0. Okay? Now we talked about that, right? So let me add my 1 here. So will that change the frequency of the cosine? No, but what's going to be introduced now that was new? the DC offset, right? And the DC offset is at which frequency?
0.
Frequency of 0. Now what's happened? Here's your plus and minus 1. That's your pi and minus pi. But now you've introduced DC offset of 1. Sorry, DC offset at omega equals 0. Okay? And now when you replicate it at 2 pi, now that peak is also at 2 pi because it's got to be periodic with period 2 pi. And there you go. So it all fits, right? It's kind of cool. Like we're not playing games. It's all there. And there's something neat about that. Yes, sir.
Another question.
Yes, you may.
If we find the period, right, we would do 2 pi divided by pi, right? That gives us, okay, so that's why it's a 1.
2 pi over pi is 2. So that's 2 samples per period. The period is 2 samples. And if you go back to the time signal and you look at this, all right, how many periods per sample? Sorry, how many samples per period? 2. That's it. The frequency is pi, 2 samples per period. What says you? Crazy times, huh? Okay.
When you say 2 samples per period, that's 2 samples per 2 pi? Or per pi?
2 pi. Right? 2 pi radians is always 1 period. So if the frequency is pi radians per sample, the first sample gets you from 0 to pi. The second sample gets you from pi to 2 pi. And that's it. That's your period. 2 samples per period. So let me at least write this on the board, and then we'll have our quiz. What I want you to think about is this. I want to just play around with a special filter, and we're going to we'll sort of mess with it more on Wednesday, like kind of how it's useful and what it's good for. So right now we've just been practicing playing around with the discrete time Fourier transform. It's a simple calculation, although it's not a very pleasant calculation, like it's not a ton of fun to do by hand. And so what I did here is I basically just had the computer calculate it for you, okay, with a loop. In practice, when you take an FFT, FFT basically is doing that for you. I just wanted to write it out so that you could just see that I'm not doing any magic here. The FFT is basically doing that loop for you automatically. Okay, now, there are, however, simpler filters, simpler signals that we can just take the discrete time Fourier transform by hand. And what I want to do is look at this one. So here's n, here's x of n, and this is just going to have 3 samples. 1 and 1. Okay, so at sample negative 1, you're going to have a 1. At sample positive 1, you're going to have a 1. And at sample 0, you're going to have a parameter that we can set. Could be 2, could be minus 3, could be 17. We're going to set it. Okay? So when we return on Wednesday, we're going to find x of omega, the discrete time Fourier transform, sorry, you can't see, for that signal. Okay? And then we're going to figure out how we can use this as a filter. And I think it'll be kind of cool. But anyway, if you want to work that at home, apply the equation for the discrete time Fourier transform to this signal. That will get you a little bit ahead of the game. I'm sorry?
That's in the n domain?
Yeah, it's starting out in the n domain, so it's already been sampled.
Okay.
And you're going to filter it.
The person will have to find x of omega?
No, that is what you're finding, x of omega.
Yeah.
You're just applying the definition of the short time Fourier transform. The discrete time Fourier transform. That x of n, e to the minus j omega n.
Okay.
Just apply it to those 3 samples. You're just summing it over 3 samples. Okay, well, quiz time. I don't think